All right, we're at 34 people. I think that's good. We're good to get started. Well, first of all, welcome everybody. This is the first workshop the Developer Student Club will be hosting at Rowan University. So a lot of you in your responses mentioned that you want to know what the Developer Student Club is. We did some extra marketing this time to some new people. So here's a brief reintroduction to the Developer Student Club. This is just a collaborative learning community, right? It's a place where we do personal projects and learn new skills together. It's a Google-backed club, right? So you actually get spearheaded by Google to start one of these, and then involvement in one of these clubs actually helps you to learn new tech and also get on the board with Google representatives. We do projects and do workshops like this one. Sometimes we do like live Google speaker series, challenges, and other events like that. We're also looking to solve community problems with software solutions. So if any of you are e-board members of a club or know of a club that could benefit from some computer science people or from some developers, direct them in our direction. By popular request, our first workshop was Python, and so that's what this is. Our second workshop is actually going to be TensorFlow. Here's a QR code if you want to RSVP to that. TensorFlow, for those who don't know, is a good way to, it's a deep learning library for machine learning. I'll be hosting that with my friend Evan Pierce. He's actually in chat right now. If Evan wants to say anything right now, now's the time. But yeah, if you want to get involved with the Developer Student Club, you should first check out our website, rowandsc.com. Be forewarned, I need to update this website with some things, but these slides will be published later, so you can click on these links. But we've got a community event platform for you to join as well, provided to us by Google, and some social media. All of that is accessible through the website. Just go on that on your own time, maybe after this workshop or during some of this writing right now. But yeah, I'm actually going to go back one slide to this QR code. TensorFlow. I know many of you want to know TensorFlow. So take a second, RSVP to this. We don't know the exact time and date, but if you RSVP, I get your email. So you'll hear about it as soon as we know, and everything's recorded. All right. I'm going to give this like maybe 10 seconds. But all of you, like by registering for this, I have your email. So you'll hear about it. Yeah, Python, as Evan just said in the chat, right, is needed for TensorFlow. So this workshop, if you don't know anything about Python, it's going to get you started. Okay. All right. This workshop is going to consist of an overview, a lot of different utilities in Python, why it's useful, things that you can do, followed by a live code-along tutorial. I want all of you right now to just understand that this is going to be a live code-along, right? You're going to have to program to learn the most from this workshop. So if you need to do any kind of weird setup, if you're on a phone, if you need to get out a laptop, or if you have an editor for Python, make sure all that's working. We're going to be using it later, but we're also going to provide you with a link that'll work. All right, so with that, I'm going to hand it off to our first presenter, Scott Zokol. This is my close friend and also a Python master. This guy has read books from like 1,000-page books, front to back, all about Python. He knows things that no one ever is going to ask about in Python. I'm going to hand it over to him right now.
Hello, everybody. Can everybody hear me okay? Just make sure before I go off on a monologue. Okay, good. All right. Well, anyone, like Suresh said, welcome. We're going to talk about Python. Let me go ahead and switch screens. Suresh, if you can hear me, I think I'm still on your screen, and I need to cast mine. There it is. Thank you. Okay, so yeah, as Suresh said, we're going to talk about Python. Obviously, talking about Python, it's a very broad topic. It's a very, very powerful tool. We can't say everything there is to say about Python in one workshop. You probably don't want to stick around for that long anyways, because I could talk about Python for a very long time. So Suresh asked me to kind of handpick some topics that are pretty essential to Python, just to kind of introduce you to some concepts that are very powerful and some things that Python does very well. So I'm going to start by giving you some context and maybe answer some questions that I've heard a lot about Python. Because Python's so popular, there's a lot of critics. There's a lot of people that say it's no good. A lot of people say Python's the only way to go. I just want to preface this that, well, I'm biased because I love Python. Programming languages are just tools in like your toolbox. There's no silver bullet I would argue Python's pretty close to the silver bullet, but there's some cases where another language would be better. So the biggest thing I hear about Python is a lot of people say Python is just a scripting language. They say it's only used for the command line. You can't really build large projects with it, but that's just not true. If someone says that, they just haven't studied Python long enough. Python is as this says, it's a general purpose language that blends procedural, functional, and object-oriented paradigms. So when you learn Python as a first language, it might be kind of confusing because where if you go into something like Java, it's going to kind of force a paradigm on you, the object-oriented one. But Python, it gives you options. You can do whatever you want. It's a very flexible language. And because of that, people think you can't use object-oriented. You can, it's just a matter of discipline because Python is just so flexible. So it's a very great general purpose problem solving tool. Because it's so flexible, you can pretty much solve any problem you want. It's very powerful. And there's a reason why so many people are talking about Python. There's a reason why it's so popular. It's because it's very flexible and it applies to pretty much anything. So it's very exciting. So why use Python? There's many reasons. I just selected 4 in no particular order. I just thought these were probably the most important. The first one is software quality. So Python has a very nice philosophy when it was designing the language. As programmers, we read way more than we write code. So Python recognized this and said, let's design a language that's very easy to read. It has a really great syntax. It just doesn't take a lot of brain power to really parse what you're reading on the screen. It's just very clear, very concise. So Python does that very well. And I'm pretty sure if you've ever seen Python code, you would agree. I hear some people call it executable pseudocode, which isn't far from the truth. It's very close to English, which is really impressive if you think about it. The second is developer productivity. This is probably the favorite benefit for companies. The most expensive cost for companies is labor. Programmers are expensive. There's a reason why we're all going to college for computer science, because we want to make a nice salary. Companies, while they love to have you, they want to make most of your time because you're costing them a lot of money for good reason. So Python allows developers to allows them to be very productive because they don't have to write a lot of code to do a lot, because Python is so concise and expressive. So there's less time writing code, and more importantly, because the code base is smaller, it's less to maintain, which is very important in saving costs. So that's very exciting. And then the next is portability. So a Python program is very portable. It pretty much can run on any machine that supports Python. And the reason why it does this is because there is a Python virtual machine. So if you're familiar with Java, you're probably familiar with a Java virtual machine. It's very similar. Python is an interpreted language. It starts with Python source code. It is then compiled down into bytecode, which the Python virtual machine will take that bytecode, and it's very simple. It just executes it as fast as it can. But because the Python virtual machine is independent from whatever architecture you're running the program on, that's the reason why it's so portable, which is very nice. It saves a lot of headaches. And again, it increased that developer productivity because you're not worried too much about being portable, which is really cool. The next point is really a big deal. So Python has a lot of built-in libraries that are very expressive. They allow you to solve problems that are very high level. There's built-in library support for things like as simple as string pattern recognition, which we'll do some later in the workshop. And it ranges from that all the way up to like network scripting. There's just so many tools, and that's just in the built-in library that Python comes packaged with. That doesn't include the third-party libraries that anybody can write. And there's just a huge ecosystem of code that people want to share. And really, there's a module for anything. There's not much you can't do in Python. And if there isn't a module that exists, it's very easy to write them and publish them yourself. So that's very exciting. So the biggest complaint, besides it being a scripting language, is that people say they don't want to use Python because it's too slow. And that is true if you want to. It is slower than a language like C or C++. But I hear that a lot, like saying Python's too slow, why would I ever use it? But for a lot of cases, the speed trade-off, the difference that you're losing when you use Python, it's worth taking that hit because the productivity and all the other benefits we just mentioned are just worth it. If your application doesn't need to run, that fraction of a second faster, then you don't need it. It's worth being able to write code that's easy to maintain than just have a few extra seconds of computation. But I'm not naive. I understand some applications need to be very fast. So that isn't the end of the story, though, for Python. It's not like, okay, if you need something fast, you can't use Python. That's not true at all. So there's two main approaches that are taken when you want faster code, but still want to use Python. So the first one is using a different implementation. So before I explain or introduce the different implementation, let me just explain what I mean by that in the first place. So the Python language, it's kind of misleading when we say Python. When we say Python, we usually mean CPython. So if you haven't heard of that, CPython is actually an implementation of the Python language. The Python language specification, which you see on the left, it's just like a book of rules. There's no actually coding being done. It's just this big document that says this is what Python is, this is what Python can do, this is what it can't. It talks about like different data structures, different algorithms. It specifies just the complete set of rules. It's just a language specification. The most popular implementation of that book of rules is CPython. And as if you can kind of guess, it's written in C. So when we say Python, we really mean CPython, the implementation of the Python language. So when people say that Python's too slow, they're really saying CPython's too slow. But that's just one of the implementations that you can use. There's another implementation called PyPy. It's actually very popular. The creator of the Python language even recommends it if you need a speed increase. So what it is, it's just a re-implementation of the Python language. It still follows all the rules in the specification. It just has a focus on speed. So the code base is different. And on average, it's 4 times faster than CPython. But there are cases, depending on what you're doing, where it can be up to 100 times faster than CPython code. So if speed is necessary, you can still use Python. You just kind of have to change your tools. And just to mention, there are many implementations of Python. There's Jython, which, as you can guess, it's Python, but just implemented in Java rather than C. There's one for the .NET framework, embedded devices, and then there's even CPython re-implemented, but with a focus on concurrency. And there's many more. I mean, you could write an implementation of Python if you wanted to, but those are just some of the more popular ones. So the next approach, if you still want to use CPython, that's fine. This is probably the most common and most effective approach. You can just write your time-critical parts, the parts in your program that need to be fast. You can just write them in C. Because CPython is the most famous or most popular implementation, writing C and wrapping it in Python is really easy. Actually, CPython encourages you to do that. It gives you tools to do that very easily. So Python is kind of acting like a control language. You get all of the benefits of Python, and all you're seeing is Python. Just in the background, it's calling the C code. And as you know, C code can be extremely efficient and run very quickly. This is actually, like I said, it's a very popular technique. One of the third-party Python packages, NumPy, just as background, NumPy is a numerical computation library for Python. It deals with things like arrays or matrices, and it has algorithms that you can operate on those matrices in a really efficient way. And all those algorithms and all those structures, all the data structures, they're all written in C in the background. It's doing exactly like I just described. And because of that, it's extremely fast. But all of that's abstracted away through just Python methods that you use when you install the NumPy library. NumPy is definitely my favorite library, but it's favorites of many other libraries as well. It's the backbone for a lot of machine learning and deep learning libraries. I'm sure Evan, when he has his talk, he might mention NumPy, or at least it'll be working in the background if you don't see it, because it powers a lot of TensorFlow. And then I know Sarosh might be using NumPy in his example when we get to some of the problems we're going to solve in the workshop. So NumPy is very powerful, and it's fast, and it's still Python. So again, the speed issue isn't the end of the road for Python. Okay, so that's enough history and like background. I'm going to go ahead and jump into some Python fundamentals. There's many more fundamentals, like I mentioned earlier. I just had to handpick a few, and then I'm going to show you some code to kind of explain the concepts a little better. So the first thing I'm going to talk about is dynamic typing. So if you haven't heard of that phrase before, it's pretty much the first thing you'll notice if you've programmed at all. If you look at Python for the first time, especially if you're coming from a C, C++, or Java background. In the Java programming language, it's statically typed. So the types are known at compile time. Anytime you want to create a variable or anything, you have to specify what kind of data that is. If it's an integer, if it's a string, have to specify the type. In Python, it's dynamically typed. So the type isn't known until runtime. So you don't have to specify the type at all. A lot of people don't like that, especially if they're used to statically typed languages. They think it's too prone for errors. But I'm going to show you that while that might be true, if you use it correctly, it can actually be very beneficial to you, which I'll explain more in a second. But before I do that, I want to explain how that works, because it's going to seem like magic. Let me move to the next slide. So before I address this slide, in Python, you can have a variable, say it's named is a, and equals the number 42. On the very next line, you can have that variable reference a string. So if you're coming from Java and you see those 2 lines of code, you're kind of like, whoa, why is that variable changing types? That's really strange. And that would be strange if that is what is happening, but that's not true. You're going to have to change your way of thinking a little bit if you're coming from Java into Python. So in Python, the types live with the objects, not with the name, not with the variable, which you can kind of see in this diagram. The variable a is pointing to some object in memory. That object in memory has 2 properties. It has a value. In this case, it would be the number 3. And it has another value, which is the type, or the attribute is the type, and it's specifying that it's an integer, or a float, or whatever it is. In this case, it would be an integer. So the type is on the object side. So when you have this variable a equals 3, and in the next line you have a equals, the string Scott, whatever, the type isn't changing in the variable a because the type doesn't exist there at all. The only thing that's changing is the reference, or that pointer. It's no longer going to point to that 3 in memory. It's going to point to a different object that represents the string Scott, which has the type string. So if you are familiar with C or C++, the references, or the arrow you're seeing on the screen right now, when we're talking about CPython, they're literal pointers running in the background. That's all they are. There's a system table that has, for each row, it has a name, which is the variable that you create. It has room for a pointer, and then it points to some object that's in memory. That's how the types are working. The key thing is to remember that types live with objects. This is a really cool design because Python will do some caching in the background. So say you have this huge Python program, and you're using the number 3 like 50 times throughout your whole program. Python's not going to create 50 different objects for that number 3. That would just be extremely redundant. What's going to happen is, because that 3 doesn't change, a 3 is not going to suddenly become a 4. A 3 is always going to be a 3. All the references of that number 3, they're all going to point to the same object in memory. So there's no redundancy, which is very nice. So Python can cache objects like that. It'll do that for small integers or small strings, and then some other types as well. And I can actually show you this in this file. Let me just make sure everybody can see that. Can you see this notebook? Is everybody good? Anybody in chat or anything? Okay, cool, thanks. Okay, so if you haven't seen this, this is a Python notebook, or sorry, a Jupyter notebook. It's still a Python script, but it's kind of like delayed execution. So you can kind of see, I don't know if anyone's used Mathematica. I'm not sure how many people are familiar with that in the chat right now, but this cell is kind of like isolated. So I can run just that cell, and then I can kind of just go through the file, and it'll kind of like slowly delay the execution. That way the whole file doesn't run, and I can kind of walk you through it. Sarosh, when he's doing his problem or his solution to the problem he's going to be solving, he's going to be using an editor where it just runs the whole thing, so you'll see both. But sometimes this is used for like tutorials, kind of like what I'm doing now, or just like scientific computing, just like doing research. You'll see these pop up every now and then, but they're very cool. So anyways, back to, I just want to show you this object caching that Python will do. So I'm just gonna, for this first cell, I'm gonna run it. A and B are both equal to the integer 42. So in this cell, I'm gonna do an equality check, which I'm sure you guys have probably seen. If not, the equality check in Python takes the two inputs, which is gonna be A and B. It checks their values, and it sees if they're the same. If they're the same, it's gonna return true. So not surprisingly, this returns true because both of their values are 42. But down here, I'm going to use the is operator. This is similar to the equality check, but it's not going to check the values. It's going to check the objects that these variables point to. So if you go back to this slide, it's checking to see if this object that A points to is B pointing to the same object. It doesn't care about the value. It just cares about what it's pointing to. So I want to show you that caching is happening right now. Because 42 is a small integer, Python says, hey, we don't need two 42 objects in memory. We can just use one and have them point to the same thing, because the number 42 is not going to change. So if I return that, it's true, which is interesting. So then I'm going to show you another example where it can't cache an object, just to prove to you that I'm not just making this up. So I'm going to have two variables, list1 and list2. They all have the same elements in their arrays or in their lists. Array, lists, it's kind of like interchangeable if you're familiar to hearing array. It's the same thing in Python. We just call them lists. So a list is it's not going to point directly to three objects. It's going to point to a collection of pointers. It sounds a little redundant, but if you think about it, it does make sense. The list is pointing to a collection of pointers who in turn are pointing to three distinct objects. So when we do the equality check, it's going to check the values of each element in both lists, and it's going to return true because they're the same and it's the same length. But if I do the is operation, it's going to return false because list1 is pointing to a collection of pointers and list2 is pointing to a completely different collection of pointers. Python can't cache the collections of pointers because lists can change. They're not going to be the same size forever. They're not going to be the same values forever. We just can't cache that. There's just no way. So if you check it, it's going to be false. So that's just kind of a proof of concept that caching works for certain like literal values, like small integers and small strings. So it's really cool. It's very interesting. That dynamic typing looks like magic, but underneath it's pretty simple. Okay, so let me go back. So before I go to the iteration protocol, there's one more thing I want to show you with dynamic typing. So dynamic typing allows us to practice duck typing, which I'm not sure if anyone's heard that. I promise I'm not making it up. It's a thing. What duck typing allows you to do is you can write code that doesn't care about the type of the object. it cares more about what the object does. That'll make more sense in a second. But when you do this, you can write code that is very abstract, and it can apply to types you didn't really imagine, you didn't even really account for when you were writing the code. So I can explain what this means. And just to clear up, duck typing, the reason why it's called that is because if it walks like a duck and it quacks like a duck, it's a duck as far as Python's concerned, or as far as your program's concerned. It's good enough. It behaves like one, so it is one. So it sounds like it's a little messy and a little too relaxed, but if you know how to use it well, you can write really general code, and you avoid writing other methods that handle special cases, and you can just write one method that handles many cases. And again, going back to the benefits of Python, less code means less maintenance, so it makes your life easier and you can be more productive. So let me just jump into this first example, which is going to be the first two cells here. So Python has a built-in method called len, stands short for length. It just takes in, well, right here it's taking in a list, and if I run this, it's going to return 3, which makes sense because there's 3 elements in list 1. But here I'm going to be passing it a totally different object. It's a string. It's the string little Rowan, and it's assigned to the variable university. So if I run this, it's going to return 5 because there's 5 characters in the string Rowan. And the reason why length or len takes 2 completely different objects is because, again, it doesn't care about the type. If it walks and quacks like a duck, it's good enough. And in this case, the quacking it's just implementing this this method called len. If you're wondering what the underscore mess is around it, it's just like a Python convention for some common functions. But the list and the string both follow the length protocol. And as far as the length method underneath here is concerned, if it follows that protocol, meaning it implements that method, it's good enough. It's good enough for the length method to accept that type and return a value that makes sense. So that's exactly what happens here. So this length method only has to be written once, and it's a very general. It can accept anything that it implements this underscore length method. So let me give you another example, because I know sometimes that one's kind of hard to understand. So here I'm going to write this function, print 2 iters. You don't really have to know too much what's going on in these 2 lines. It'll help if I just show you an example really quick. So I'm going to use this list 1 up here that we used, 1, 2, 3, and then list 2, which contains 4, 5, 6. And I'm going to pass both of those into print 2 iters. I'm just going to go ahead and run that. And as you can see, this is why I said you didn't really need to know exactly what's going on, because you can just see it. It's going to step through each of those lists and just print out the elements. So it goes 1, 4, 2, 5, and then 3, 6. And it just walks through them just as in pairs. So this method that we wrote enables duck typing. It's very abstract, and I can show you by defining this other type tuple, which is 10, 20, 30. I'm going to pass it in with our list 1. So these are 2 different types, but it still behaves the same way. Even though it's just 2 completely different types, they both behave, which I'll get to in a second. They both are following some protocol. And then, so you might think like, okay, tuple, that's kind of similar to a list. That may not be too shocking, but again, you just don't know. Your code's going to last a very long time. There might be data types that you just didn't consider, or just maybe they weren't even accounted for yet. So I'm going to load this file. It has 3 lines. I just copied and pasted in here and then commented it. But it's actually just this is what's in my file.txt. And then obviously there's no comments. So it's just these 3 lines. I'm going to go ahead and open it up in read mode and store it in the file. Store it in the variable my file. So I'm going to go ahead and do that. And then I'm going to go ahead and pass it to our function, the list 1, which is the 1, 2, 3. And then when I run that, you can see this method, it works for files, which is probably something you didn't consider when you were first writing it. You were just writing it abstractly, kind of just thinking maybe it's going to be for lists. But you can see Python allows you to write in such a general way that it can apply to files as well, which is really cool. It just kind of keeps going from there. You can account for so many data types, all because they're following a certain protocol, which is really interesting. So kind of transitioning into the next topic. So the method that we just implemented, the protocol that I was following is called the iteration protocol. And it just so happens the next thing I'm going to talk about is the iteration protocol. It's almost like this was scripted. So the iteration protocol is pretty simple. It's a very common pattern in Python. It's pretty much just any object that kind of has a collection of elements. And if you call the next method, which is right here, I'm not sure if you can see my mouse, but it's right by that number 2. If you call the next method on that iterator, it's going to give you the next element, which is a pretty, if you're familiar with any kind of programming, it's kind of a familiar concept. But in Python, it's made specific. It's a official protocol that you can implement. So you'll see some methods will say, argument A is any iterator, argument B, is any other iterator. And when they say that, they mean it's any object that implements the iteration protocol. So if we go back to the code we had, that's exactly what's happening here. A and B are following the iteration protocol, and that's the reason why all of these applied to our function, because list, tuple, and files are all iterators. An iterator is a very common type, so the function could apply to even more things. But I want to show you some more examples of kind of diving in what the iteration protocol is. So I will switch over to this file. So again, I have my list1, which has the elements 1, 2, 3. So Python loves iterators, and it'll give you some tools or some syntax, I guess, to work with them in a more concise way. So I'm kind of going to skip down to this code down here. It's a pretty common for loop. It's for I in, and then whatever goes after that in just needs to be an iterator. So what I'm doing here is just to make it explicit, is I am calling the iter function on the list, which will return an iterator to me so that I can iterate over it. I really didn't have to call the iterator there, because a list will do some things in the background where if you just give it the list variable, it'll return the iterator for you. But I'm not going to get into that because it kind of complicates things. But just know that I could just say for I in list1. So what that does, it just calls next on that list1 until an exception is raised. And the exception is called the stop iteration exception. Again, it's all following the iteration protocol. Objects that implement the iteration protocol will support the next method, and they'll raise a stop exception when there's no more elements to feed. There's no next. It kind of reached the end of its collection. So Python will allow this for loop construct to keep running until it hits that exception. So it's a real easy way just to go through everything in a collection. Really what happens in the background is this. This is what Python will do when you run these two lines. It'll get the iterator. While it's true, it'll try to get the next from that iterator, which is it1. If it hits the stop iteration, it'll just break. And that's exactly what happens behind the scenes when you call this. And if I run the manual iteration, you'll see it loops to the list 1 through 3. That works. But why use that when they give you this really clean syntax that will do the same thing? So that is the automatic iteration syntax that Python provides. And then I'm just kind of show you, again, like I said in the previous file, tuples, they are also iterators. So it's going to work just as well. And here you can see I'm not calling that iter function. I'm just calling a tuple, and it iterates right through it, again, because it follows that protocol. I want to show you a little more complex example. So dictionaries in Python, if you're familiar with Java, a hash map, it's just a key value pairing. It has a really efficient lookup speed. If you go in later courses, I know we have a lot of beginners here, but when you study algorithms, hash maps are very powerful when it comes to time complexity. And Python, just so you know, if you're asked this in an interview, has a very, very efficient implementation of hash maps, or whatever you want to call them. And they perform very well. The lookup speed is about constant for most of the time. It's really impressive. So anyways, that's the dictionary. I defined some key value pairings, and I just want to iterate over them. I just want to show you that dictionaries can act as iterators too, but because there's two values now, it can be a little more complicated, but Python gives you methods to do whatever you're trying to do. So I'm just going to iterate over dictionary 1, and by default, it's going to iterate over the keys. So you see it only does dog, cat, and bird. If you want to iterate over the values, you just call the values method on the dictionary, which will return an iterator, but this time it's just going to be for the values. If you want to do both, you just do items, and then it'll give you a tuple of the key value pairs. That's just a common pattern that you'll see, so it's good to know that dictionaries aren't excluded just because they have it's a little more complicated with the key value pairing. This one I'm just going to throw in real quick, just because Sarosh will be using it later, and I just want you guys to get more familiar with it. It's pretty simple. That's the nice thing about Python. It really just reads like English sometimes. A common pattern you would want to do is you want to iterate through a sequence of numbers, and there is this range method which returns an iterator, which is why it's in this section, because it's just another iterator, just like we've been using before. It takes a parameter. So if you only specify one parameter, it's going to default the start range to be 0, and then the end will be the one that you supply. So I'm just going to go ahead and run it so it makes a little more sense. It's just going to give me a sequence of numbers. And because 0 is implied, it's going to start with 0 and go all the way up to the end, which is 5. But the end number is always exclusive, so it's never going to be included. But it's a quick way to iterate 5 times, which is really easy to construct, because if you just want to iterate 5 times, you just write a 5, because it's still going to be 5 iterations because we're starting at 0. If you want a certain range that doesn't start at 0, you can always do that. You can just pass in 2 parameters. The first one will be the start, which is inclusive, and the second will be the end, which is exclusive. The range is a really common iterator. You'll see that a lot. That's a very common pattern that you would want to do. Okay, so that is the iteration protocol. And the last thing I'm going to talk about before Sarosh kind of implements a solution in Python for a well-known problem, I want to talk about comprehensions. Comprehensions isn't something you would learn maybe when you're brand new to Python, because the syntax can be a little intimidating at first, but it's really, really powerful because it can cut down a lot of lines of codes in a really clean way. It can be very expressive to do complicated things in a very, very simple way once you get used to reading comprehensions and writing comprehensions. So just as a definition, a list comprehension is Python syntax for creating a list, pretty much. And I'll show you the syntax in just a second. Okay, so I'm going to define a list that's going to have the elements 1, 2, 3, 4, 5. And before I get to the comprehension, I just want to show just a pattern. I want to create a new list that's list 1, but it's just 10 added to every element. So it's really simple. I just create a new list for result. And then for each element in list 1, we're using that iteration protocol that we just went over. I'm going to take each element and I'm going to add 10, and then I'm going to append it to our result, and then I'm going to print the result. So you would just get what you would expect. So a better way to do this is to write a Python list comprehension. It's pretty much the same thing. The syntax just looks different. So we're going to define our result, variable, and we're going to write the comprehension. The syntax goes like this. You're going to have brackets surrounding the whole expression. As you'll see if you read more about comprehensions, there's comprehensions for tuples, sets, dictionaries, and things like that. The brackets signify that we're making a list, and we're not making a dictionary, we're not making a tuple, we're making a list with the brackets. The first part, which is I plus 10, is your expression. The next part is going to be the for loop, and then it's going to be the variable in the iter, which stands for iterable, that we already covered. It's just going to run this expression for each element inside this iterator. And then after it runs this expression, it's just going to, that return value, whatever is the result of that expression, is going to be added to the list. So for each I in list 1, it's going to add 10. And then it's just going to print the result. And you can see this does the exact same thing. So why do we care about this? It takes 4 lines of code, or 3, and wraps it into just 1 line. And once you're used to reading it, it's easier to understand. You're used to seeing the patterns. You know what you're looking for. But more importantly, when using CPython, this is a lot faster than a for loop because it's a very specific syntax. CPython just knows how to handle it in a certain way, and it can make some optimizations to run that code really fast. So comprehensions, for the most case, are faster than for loops. That's just something to keep in mind. So you're getting better syntax, and you're getting better performance. So for the rest of this, I just want to show you that expressions, there's an extended syntax you can use to do a little more complicated expressions, which kind of get more complicated if you're going to write it out as a for loop. But if you're writing as an comprehension, it's not that bad. Okay, so what we're going to do here is we're going to loop through each element in the list. If it's even, we're going to square it, and that's going to be our list. As you can see, that's what this code does here. So it takes the even numbers of this list up here, and it squares them. So if we want to do that in a comprehension, we're just going to have our expression, our variable. All this part we already know how to do. That's highlighted. We're going to add like a kind of a filter to the end, which is just an if statement. So it's only going to add that value to our result array if that condition is true. So it's going to square it for each I in our list iterator if I modulo 2 is 0, which, if it's even. So if we run that, it'll give us the same thing. So it's a little cleaner, and we know it's faster in the background, which is nice. So I'm going to show you a nested loop, just to show you that even nested loops can be done in comprehension as well. So I'm going to take my list from before. I'm going to have my list 2 here, and then for each element in the first list, I'm going to loop through all the elements in the second list and return that pair of values. So if I run this, you'll see for each 1, I get ABC. For 2, I get ABC, all the way down to 5 ABC. So it's kind of a silly little program, but I just want to show you that nested for loops aren't that bad in comprehensions either. So we're just going to return the pair for each I in list 1 and for each j in list 2. I mean, it's really kind of just flattening the for loop. If you think about it, it's not that difficult, and it'll produce the same result. So there's that. And then I want to show you where I think it's really impressive when you're writing functions. So we're going to go ahead and write the intersect function, which is going to take, here I'm using strings, but again, it can be anything. It can be any kind of iterable if we wrote it correctly. And it's going to take the intersection between those 2 strings. So it's going to return what characters are common between A and B. So what it's going to do is going to create a result, an empty array. And for each x in A, if the x is in B, then add is the result. It's pretty simple. So then if I call it on these 2 strings, we're going to get SAM, which is common because P and C are not. So that's how we intended it to work. But with a comprehension, you can write it in just 1 line, which is really great because if you're looking through your code and you have a lot of methods you implemented, you can see that you have a function called intersect, and then it's almost just right here in a 1-line definition. It's almost, it's just very simple. It's all together and it's very compact. And all we're doing is, we've seen this before, x for x in A, if x in B, which is pretty much the same exact syntax here, just converted to a comprehension. And again, not to be a dead horse, but it's going to be faster too, which is kind of why wouldn't you want to write it in a comprehension? And it gives us the same value. The reason why I bring up comprehensions, it's not something you bring up to a beginner because you kind of want them to get used to the for loop syntax, especially if they're new to programming. But comprehensions are used in a lot of open source Python code, and you're going to run into it whether you like it or not. At first, I didn't like them when I started learning Python, but after I kind of played with them and realized what benefits they bring to writing clean and more elegant code, I started to like them way more. And then also when you're reading source code, when you see them, you don't have to go to Stack Overflow every single time and figure out what's going on. So I just wanted to expose you to those comprehensions as well. And then right before Sarosh takes over, I want to work on a problem with you guys, a real simple one, because I did say I wanted to show you some built-in libraries and some text pattern recognition, which is a very common operation in programming in general. So let me go ahead and describe what we're going to do, and then I'll show you a quick solution. So I have another text file. The text file is just going to be this part. It's called letter.txt. And you can kind of see it's kind of like a letter to someone. But I have these, like, I'm going to call them tags. It's 2 braces and then some kind of like descriptor in the middle. And what I want to do is I want to input values for the person, the adjective, and then the author into this text file. I want to overwrite it with values that I specify. And we're going to do that with pattern recognition using regular expressions. I'm not sure. I know we have computer science people and I know we have engineers. For the computer science people, I'm not sure if you've taken foundations or maybe you've just heard of regular expressions, but you're going to run into them there. It's a very common concept to learn. So I do recommend learning it, even though it seems a little intimidating at first. It's very powerful. And this isn't just a Python thing. You're going to see regular expressions pretty much in any language you go to. And a lot of like conceptual processing has to deal with regular expressions. Okay, so let's go ahead and import the regular expression library, which is just RE for short. And then I'm going to go ahead and open this letter.txt file. Something I didn't mention earlier, or I guess I kind of showed you, the open method is an iterator. And when I call this read method, it's going to just iterate through the whole thing and just kind of expand it all for me. So I don't even have to write a for loop at all. The read's just going to go ahead and just go through and get all the lines, and then we're going to store it into this letter variable. So it's even cleaner syntax, which is really nice. So I'm going to go ahead and do that. So I'm going to create a dictionary similar to the one we saw before. The key to the dictionary, so it's going to be key value pairing. The key is going to be the tag that I want to replace. So for every tag, I want to replace it with my value. So I'm going to write a letter to Sarosh. That's what I'm trying to do. So yeah, for person, I want to replace it with Sarosh, adjective, intelligent, and then author, Scott. So I'm going to go ahead and just define that because we're going to be using it later. So you can see already that the program is not that long. It might seem like a complicated task, but you can write complicated solutions in just very few lines in Python, which is really exciting. So let me just break down this line for you. So the whole expression, we can see we're doing a list comprehension, which is the whole thing. And it's going to assign that list to tags. So we know tags is a list. We're going to go ahead and start. We're kind of read this left to right. So what's going to happen, we're going to use the regular expression library, and we're going to find all the tags using this regular expression pattern. Now, if you're not used to regular expressions, it's going to look kind of complicated, especially down here. Don't be scared. Once you learn this, if you're CS, you'll learn in Foundations. If you're not, I would recommend learning about them. The syntax is pretty simple, and once you are used to seeing regular expressions, you kind of like are able to read them faster. It's not just like a bunch of random symbols as it might look like now. But in short, what it's going to do, it's going to look for these 2 kind of like delimiters, the braces we're using to specify the tags. And this dot star just says capture everything in between those two double braces. That's all that pattern's saying. Regular expressions allow you to specify a complicated rules for search in very few characters. It might seem like there's a lot of characters down here, but if you imagine programming that without a regular expression, you would have a huge program. So it's very concise. Even though it's ugly, it's very powerful. And there's a reason why every language uses regular expressions. So what's happening in this re.findIter, it's going to use this pattern and apply it to the letter.txt, the letter file we read into memory here. And it's going to return a bunch of matches. A match is just an object that's defined by the regular expression library. So we're going to have each match, and then if you're thinking about our list comprehension syntax, this is going to run for each match. This is our expression. Match is our value, and then this whole part is our iterator. So it's just the same thing we're doing before. It's just those parts are a little more complex now. But this is the expression it's going to run for each match object in the results from the search. And it's going to have these values. Each match object has a start value, which is what's returned by this method, and it's going to have an end value, which is returned by that method. Those return the start index and the end index. So it's going to find a tag here, and however many characters this is from the start of the file, it's going to say this is the start and this is the end. And it's going to do that. So our result's going to have 3 matches, and it's going to give me the indexes for each beginning and ending of our tag. So as we're iterating through and we're getting those indexes, we're going to access this letter, which is now a string. We read that file into memory and it became a string. We're going to index that start and that end, and we're just going to extract it. So that's going to be the result of our expression in this list comprehension. So all that to say is, for each tag it finds, it's going to return this person tag, this adjective tag, and this author tag. That's going to be our list. It's just going to be strings. It's just finding the tags and then extracting them from the file, which makes sense why the variable is called tags. So if I run that, done pretty quick. So now we just need to take out the tags of our file and input whatever we want to put into it. So we're going to do that. We're going to just iterate over each tag in tags, which again, tags is an iterator because it's just a list. This list comprehension just builds a list. And as we know, lists are iterators. So as we iterate through it, we're going to get the tag value. This expression looks complicated, but all it's doing is it's removing these braces and the space, and it's just getting the kind of like the name for the tag. The reason why it looks complicated is because, say like the tag didn't have a space here, it would still work. Or say, it had multiple spaces, it would still be able to detect the name. And you can kind of see what's going on. It's detecting the double braces, it's detecting 0 or more spaces, and then it's kind of doing the same thing for the closing. So what it's going to do, it's going to find those braces and spaces, and it's going to replace it with nothing. And it's going to run that for each tag value. For each tag. And we're going to get the tag value, and the tag value is that named attribute inside this whole expression. So the tag value for each iteration is going to be person, the string adjective, and the string author. So the reason why we need to get the attribute is because we need to access what values we're going to be replacing in our dictionary. So here I'm overriding letter, and I'm going to have it replace the tag, which is the whole thing, including the braces, with the tag value key inside our values dictionary. So for example, it's going through the first iteration, it's going to find this person tag, it's going to replace that whole thing with the person key inside our values dictionary, which is Sarosh. So if I go ahead and run that, and then print letter, it's going to input all of our values. which is what we want it to do. And then we can always change our values, but more interestingly, I can change, well, actually, to keep it simple, I'll just change this. I can make it a letter to myself. Sorry, Sarosh. And it would implement that, or maybe not. There it goes. There's the thing with the Python notebook sometimes. The state can get a little weird because you're executing parts of the file at the same time. So sometimes you just have to run through the whole file again. But you can see that it just replaced Scott instead of Sarosh. So now I'm talking to myself. But that's that. That's just a simple problem you can do with Python using its built-in libraries, its list comprehensions, its iterator protocol. And you can do it very concisely without having to write a 100-line program. I see a lot of beginners in Python. They'll create really complex solutions to kind of problems that are, kind of difficult. But as you use Python more and more, you'll be able to refine how you write solutions and write them in, more concise syntax without it being too complicated. You find how to write things in a clean way, and it just takes practice. But that's it for the Python fundamentals. Sarosh, you're good to do the percolation problem.
Hey guys, you hear me? Just let me know right now in the chat. All right, awesome. Okay, we're going to be tackling the percolation problem. I'll be going through this solution. I'm not a Python expert. I just really like Python, and I like to hack all my solutions together using Python. So in physics, chemistry, and material science, percolation refers to the movement and filtering fluids through porous materials, right? So if you imagine like water going through coffee grounds or water flowing through rocks, right? We can model this behavior using a grid, right? Where black squares represent rocks or things that are closed, and white squares represent squares that are open. And water flowing just means finding the path from all the open squares on the top layer to any open square on the bottom layer, right? So this is going to involve making boards, right? Here's another image of what this model would look like. Water is flowing in through the top, and it's going to everything that's open at the top, and these are all going to flow. Diagonals don't count, by the way, until it can flow out to the bottom. So for example, this third board here, this one percolates, these first two don't. Now, the big question we want to ask, like the question that we're trying to answer here, is what proportion of the squares need to be open generally for a system to percolate? And we're going to experimentally calculate that. This program is going to have three basic components. We're going to make a board simulator. We're going to do some fancy programmer stuff that you'll see to figure out how it works. And then we're going to do a driver that'll keep doing it and collect data for us. Okay. So we're going to be using arrays for our board simulator. A 2D array is going to represent our board. If it's a 0, it's a closed cell. If it's a 1, it's an open cell. So for example, here are a bunch of zeros, and they're all black. And then here we have some zeros and some 1s. And the blue here is just representing the water coming in, but these are also white squares that are open. Okay. Now the thing is, we wanna be a little careful here. I'm doing a 2D implementation because it's more intuitive. I'm giving you an n-by-n grid. It's a little bit more. It sounds like a 2D array problem, so that's why I'm using a 2D array here. But there's some things we're gonna have to be careful of, right? Like if you say in a 2D array board at x, y, and the board is a 2D array, that's not the same thing as the coordinate x, y from like a Cartesian coordinates top left, right? Board at x means the x element, so that's an array, right? If you stack these arrays on top of each other, that's how far down you're going. And the yth element means how far across you're going. 1, 0 versus board at 1, 0. These are actually reflected over the diagonal, right? So we're going to have to keep track of that first of all. And then I want to also talk about what it would look like if we did this using a 1D array implementation. So if we took all of our points and mapped them into a 1D array, right? We've got n squared points, but we're including 0. So it's 0 to n squared minus 1. And this is what the array would look like. Notice at the end of this, you're going to realize that a 1D array implementation is actually more efficient and better for what we're going to be doing. But for now, I'm going to go with the intuitive approach just because it lets me show off more Python. But I want to show you real quick how you can go between these two implementations. Notice this left-hand column. Here we have a 4x4 grid, right? This is a 4x4 grid. Notice the left-hand column. These are all multiples of 4, right? So if I want to figure out like what 5 is, right? I need to somehow generate the second array. So the value 1, because 0, 1, 1 is second value, and the second element, right? Notice that the number 4 evenly goes into all the elements in a row the same amount. So if I do like 5 floor division 4, and that's the element right here, I'm going to get 1. And all things in this row are going to be the same, right? 5 floor division 4, right? So 4 goes into 4 exactly evenly once, and 7 evenly once before this row where it's going to go in twice. That's a check for getting the row. And then we can use some modular arithmetic to figure out how far across or which element in this array that we're going to need. So if I have the element 5, that's the first element. I have 1 over from a multiple of 4. So that's going to be 5 mod 4 is equal to 1. That's how we're going to be going between these two implementations. And in fact, this 1D implementation in the background is what we're going to be using. Okay, I told you all that we're going to be programming this. Okay, go to this website, REPL.it, languages Python 3, or just go to Google, type in Python editor, look for the link that looks like this. It has all the libraries we're going to be using already loaded. There's no GitHub to fork from. There's nothing you need to do. You're just going to be typing along with what I'm doing, offering suggestions in the chat if you want to, and it's going to be a good time. The default setting is light theme. I'm going to show you how to go to dark theme over here. You see my screen. This is my editor. In settings, second line. This is how you go to dark mode. A lot of you on the Dart and Flutter workshop were upset about light mode. This is how you go to light mode or to dark mode. Okay. So let's code a board. Let's code a board simulator. And we're going to be hacking this together somewhat. I'm going to import some libraries I know I'm going to be using. So follow along with me as soon as you have the editor open. We're going to import NumPy as NP. We might be using it, we might not, but I always start by opening NumPy because I know I'm going to find a use for it. Okay. I want to make a function that will generate boards with a certain amount of open squares. So I'm going to make a function called generate random board. I'm going to give it a parameter n. Notice for you Java nuts out there that I didn't specify what n is. This is what Scott was talking about. I can just say n, right? And if I give it a number, it'll figure out that it's a number. I need to tell it that it's a number immediately. And I'm going to give it p, a percentage for how many of the squares I want it to open. I may or may not end up using p. I might just use this as it is. This is bugging. It keeps repeatedly running, so I'm actually going to refresh my page and then start over. Or not start over. It actually saves everything I have because I registered an account with this. But OK. So I'm going to generate this function. I'm going to make this function to generate boards. OK, we need a 2D array, n by n. I need n arrays all of length 0. You can't see the code. OK, let me see if I can make the font bigger. OK, if not, I can probably just zoom in directly. OK, do you guys see it now? Or should I zoom in some more? All right, I'll zoom in some more. Oh, there's a font option. I'll make it large. All right, and then I'll probably zoom out a little bit to compensate. OK, now we're here. Now there's a few ways that I can make an array of zeros of all zeros, right? One way that I really like, right, is using array multiplication. I can make a board or an array with an element in it, and I can multiply this by some number. What this will do, this array right now is an array of all zeros of length n. You could just do that automatically in Python. And I can do a little hack here where I surround this whole thing with a brace and then multiply this by n. So this means make me an array of length n with entries, all of which are zeros and n of them. And that's one approach. I'll just comment that and leave that as an option for you guys. There's another approach as well using NumPy. I can do board is equal to NumPy dot zeros, and I can pass in n comma n. This is going to make a NumPy array of a 2D array of zeros and zeros. It's going to give me a matrix. That's another option. I'll also leave this commented here if you guys ever want to do this. And then, of course, you can just make it manually, which is what I'm going to be doing just because it lets me show off some more Python and some tricks, right? OK. So this is an array with n arrays in it, all of which are populated with n zeros. I'm going to make a double for loop. For I in range n, this for loop is going to be the outer structure of the array, right? So I know I have n arrays in it, so I'm automatically going to append to the board an empty array. And then I'm going to make a second iterator, or a second number, that's going to go all the way up to n, adding zeros to the array that I just put in. So for j in range n. And then the array that I'm going to be grabbing is the array that I just put in. So board at I, and I'm going to append to that a 0. Okay, and that's going to give me a board. That'll give me a board. Now, I want to open random squares in here. I want to open some percentage of the squares in here automatically. And so one way that I can do this, well, first of all, if p is 0, as in I don't want any open squares, we're done. Just return the board. Otherwise, I need to generate numbers, right? Random numbers that are going to open squares. But I don't want any repetition. If I've already opened a location, I don't want to open it again. There's no way for me to do that. And so what I'm going to do, right, we've got a couple of options. Now, I could keep an array of all the things that I've already opened, and then every single time I make a new value, check against that array. Or maybe I can come up with some kind of index math that will repeatedly give me new numbers. Or maybe I can read the random library. But I'm going to use a really simple approach right here that I'll show you guys. Import random. We're going to be using random. I'm just going to keep it as random. I want to think about this as a, in the worst case, right? If I put in p equals 100, I'm going to be opening all the points. I'm going to open every single location in the array. And so here, what that means, in some sense, I'm iterating all the possible values of the array, but in random order. It's not that I'm generating random numbers. It's that I'm generating random values, right? Or a random order of all the things that exist in this array. And so one way that I can do this, I can make an array called spots to open. And what I'm going to do here is I'm going to make this a list of size n squared. Right? And this is what I mean by it helps us to think of this as a 1D array. I have 0 through n squared minus 1 elements. The range operator, as Scott was saying, is not inclusive of this value here. So it's 0 to n squared minus 1. And you know what I can do to this list? I can just shuffle it. So I've got an array here, and all I'm going to do is shuffle it. And this will give me, let me see if I can make this a little bit smaller. Right, okay. Now I've got an array of all the elements that could possibly be in my board, but in random order. So now if I traverse this array, it's going to give me a location to open for every element that I have in here. Okay. Now, the thing here is I want this to be, I only want to grab p of these, right? I only want to grab p percentage of these. So there's a function called sample, right? From the random library, right? Random.sample. And what this function does is it takes in an array and an integer value, or an integer value, and it'll tell you how many elements, like take a random sample of this array of this many elements. That's all that means. I don't have to write it myself. I can just import this library, another thing that we were talking about, right? So now I'm going to re-initialize spots to open as a specific sampling of this. Spots to open is equal to random.sample. And now I'm going to give it this whole thing, this function, right? Random.shuffle of the list that I already have, right? Like this. I'll copy it, put it into here. And I'll just get rid of this because I just wanted to demonstrate there, right? And then how many of these do I want? Well, I want p times the length of the array, right? So I'm going to pass to an integer, and I'll do p times n squared. Now in Python, to square a number or exponentiate a number, it's just double multiplication. I think that's really elegant because, you know, for integer values, exponentiation is repeated multiplication. And so you just put 2 multiplication signs. And this will give me, if my syntax is right, a random sampling of this array in random order, right? I don't actually have to do random no shuffle here. I could, because I'm already taking a random sample. I could just do list, right? Because it's automatically taking a random sample. And so from here we can continue. For every spot in spots to open, we want the which array that it is. This is the part where we're going to be using that index math that I was talking about. The array that I want is equal to whatever the spot is, floor division n. Right? As we were talking about earlier, floor division just means don't give me like a double or a float. Just give me like the largest integer that will go into this number. And the element of the array is going to be this number mod n, just like we talked about. Okay. We're going to set that value, board, the xth array at the yth value, equal to 1. And we're just going to do that throughout the board. At the very end, we're just going to return the board. All right. So first, let me just print this and make sure that it works. And if it doesn't work, we can do some debugging. But if you see any errors, or Scott, if you see any errors, just type it in the chat and I'll take a look. Okay. We're going to print generate random board. I'll make a 5x5 board with half the squares open. If I run this, first I just wanted to give me the board directly. Okay, I didn't give it an argument sample. Okay, so let's see here. What's missing? I gave it a list. I gave it this range here. Okay. Too many parentheses. That's the problem. I want it a list of range n squared, and I want to take this many values from it, p times this many, and then here I'm going to finish off the array. Let's try that. Okay. One more. Okay. Okay. Let me cross-check this. See, I prepared for this. I have a working one written. It's probably just my syntax that I was typing really quickly. But this array, let's see what the difference was. I see. Okay. And here we've got an array, right, of 5 arrays, all of length 5, with 50% of them open. Now, I actually want to show this to you as a picture, like a nice picture. So, there's a library for that too. I'm going to import matplotlib.pyplot PLT. If you want to know how I figured this out, I literally just Googled heat map in Python, and this is what comes up. And the command you're going to be using, plt.imshow. And then I'm going to pass in the board that I just made. So let's generate a random board, n equals 5.5 open. And then you have to specify some other parameters as well. So CMAP stands for color mapping. This takes in a string that's going to tell you what this will look like. And I'm going to make it hot. Now, fun fact, if you actually mess this up, if you put in a color mapping that isn't valid, it just gives you a list of all the valid color mappings, and then you can fix it very easily, as opposed to some kind of other funky error that you don't know how to deal with. Okay, CMAP is equal to hot, and interpolation is equal to nearest. This interpolation value, don't ask me what this means. I literally grabbed this line off Google and it works. That's why I love Python. Okay, plt.show. Okay, if my syntax is right, I should be okay. Run it. Now what's really cool here, it gives me this error from matplotlib, right? But it actually has it. There's no problem. If I just show you this graph, give it a second. There you go. Here's half the squares open on a random board. And this is the trick that we're going to be using to generate our boards as we continue. Okay, great. We have a way of generating boards now. That's cool. I'm going to leave this PLT thing up here for when I use it later. We've got a way of generating boards. Now we just need to find a way to figure out if it percolates. So to check if a board percolates, we need to know if any cells in the top row connect to any cells in the bottom row. Let's think about what that would look like right now with everything that we have, right? Let's take all the open squares, the first open square that we find, and then maybe we'll see how many rows, how many squares in the next row are open that are connected. Then in the next row, then in the next row, and do this side note. It was matplotlib, matplotlib dot pyplot. I'll put it in the chat. Okay. And I want you to think about what this would look like. It's like a depth first. Okay. You should be annoyed right now at the prospect of having to write this, right? Do I have to backtrack? Do I have to do any kind of brute? It's so much work. Like, this is one of those problems that, like, if you're confident and used to writing in programming languages generally, and it's annoying. So we're going to use a bit of a trick. We're going to reduce this problem to a graph problem. Right? Instead of all that, we can think of this as a union find problem. Now, what is union find? Well, given a graph, right, of n points, how can I find out if any 2 points are connected? And if they are connected, how are they connected? And finally, what does it mean to connect in this way? So notice something, right? I just had a speaking error here, right? If I look at this graph over here, and my only question is, are any of 2 points connected? Say, are 0 and 2 connected, or are 1 and 5 connected? I can rationalize this to saying that they share a point in common. That's what it means to say they're connected, or they're connected to each other directly. So in some sense, I don't care what the path between 1 and 5 is. I just want to know if they're connected generally. So I can use a little bit of a trick here. I can store the parents of each of these arrays, of each of these points, right? And so for example, the parent of 2 is 0 and the parent of 1 is 0. And so long as I do this correctly, so long as I go in the right order, and so long as I keep track of everything correctly, this should work. So let's take a look at what I mean here. At the start, with nothing connected, all the points are their own parent. So if 0 is not connected to anything, its parent is 0. So that looks like an array of 0 through 5. What this means is the indices of this array are referring to the nodes, and the value is referring to what its parent is. So at the very beginning, 0 is its own parent, 1 is its own parent, 2 is its own parent, etc. If I union 0 and 1, right, I'm going to go left to right. So I'm going to make the new parent whatever the right value was. The parent of 0 is now 1, and so this 0 turns into a 1. If I union 2 and 4, same thing. This 2 turns into a 4. If I union 2 and 5, now it's interesting. Now every single place that I had a 2, or whatever the parent of 2 was, which was 4, I'm going to make that into a 5. So now everything is connected to 5. And finally, if I union 0 and 2, this 1 should change to a 5. Does that make sense so far? Let me know if you need any clarification in the chat right now. But all I've done here is I've created this graph as a union find parent array. The way that you read this, 3 is by itself, and everything else is connected to each other with a parent of 5. The parent always just turns into whatever the last union I did was. Okay. I'm going to give like 5 more seconds, see if, account for ping, etc. See if any replies come in. All right, we're good. I'm gonna let's code this. Let's make a very basic equivalent of this graph bookkeeping thing that we're going to be doing. Okay. So first things first, I need to initialize a parent array. Right. So let me define initialize. It takes in n. It's going to make a parent array for a graph with n elements in it. All I can do is use the exact same trick I used earlier. I can return a list of the range iterable, not rage, if I can learn to spell, of size n. It's going to be an array from 0 to n minus 1, which is exactly what I'm looking for. Okay. If I ever want to find out what the parent of a certain node is, I can call this a find function. I should pass in the node that I'm curious about. Let's call it x, and the parent array. Now, my array is keeping track of parents, right? So all I need to do is return whatever the parent array has stored at index x, and this will tell me the parent of x. I want to find out if any 2 nodes are connected, x and y. I pass in x and y, the 2 indices, and the parent array. They're connected if they share a point in the middle, but every time we union 2 arrays, we change whatever the second value was to the parent. So if 2 nodes are connected, they share the same parent. That's the sleight of hand trick we're going to be using here. So we're going to return parent at X equals parent at Y. So if these two nodes are connected, this will evaluate to true, and it'll tell us that they're connected. And if they're not, if their parents are different, it's going to evaluate to false. Okay. Finally, the hardest function we need to write here is union, right? So union. I want to union X and Y and update the parent array that reflects this. The union X and Y, I need to update everything that has a parent of X to the parent of Y. And that basically reflects that they all have a common point. And so first thing I want to do is I want to grab the parent of X. So the parent sub X is equal to, did you guess it? Parent X. And I want to grab the parent of Y, and this is parent Y. Now, if they're the same thing, if they're already the same thing, they're already connected. I don't have any work to do. So if parent X equals parent Y, let's get out of here. We're done. It works. You can just return nothing if you want to. I'll return a 0 just to be, I don't know, proper. If that makes any of you happy. Otherwise, we have some work to do. I have to go through the parent array and update every single thing that has a parent of X to parent Y. So for I in range parent len, right? Take the len operator of the array parent. All right. If parent at I is equal to the parent at X, we're going to make it the parent of Y. Don't worry if anything's wrong. You're going to get this code yourself at the end. I'm going to send out a mass email. So parent at I is now equal to parent Y. That's it. All we have to do. And then again, just for elegance sake, I'll return the board here after I do this, or the parent array here after I've done this. All right, let's test it. Let's see if this does what we think it does, right? Let's define a testing function. We'll take an inputs, call them X. Take an user input in Python. It's very easy. You just do X equal to input, and then the prompt that you want to give the person. So the prompt here is how many nodes, and that's my entire prompt. And then this is going to come in as a string, right? It's going to take an argument from the console as a string, and so we need to turn this to an integer before we initialize an array of that size. So our test array R is equal to initialize int X, like that. Check the chat real quick. It's been a minute. Looks like we're okay. All right. Now, while this input is not equal to whatever is not equal to whatever I feel like, we are going to make unions. We're going to keep prompting for points to union, and then we're going to print the array to make sure it's doing what we want it to do. So we're going to update X to the input of union X space comma Y colon. This is the prompt. And now what I'm going to do here is I'm going to show you guys how to use delimiters in Python. So if I do dot split, this is a string. I'm going to split this string based on comma spaces. So if I do like 5 comma space 2, it just reads 5 2. The first element of this array, right? Remember, string has come back to being arrays. The first element is going to be 5. The second element is going to be 2. So that's a really easy way for me to do this. And now I'm going to do union. I'm going to make an integer. I'm casting integers. Remember, this is a string array right now. X at 0, comma, int, X at 1. There we go. And then we're just going to print the array, make sure we're okay. Okay, and run test. Okay, we run tests and hit run. It's still upset about matplotlib, even though it works. Okay, let's say I want 5 nodes. I want to union 1 and 2. Okay, I didn't give it the parent. I didn't give it the parent array up here. I'm doing a union call, but I didn't give it. Remember, if I do a union, I have to update the parent array, and the parent array here is R. Okay, do this again. That's all part of the process. Like, I'm giving a workshop on this thing that I've done before. I'm still going to make mistakes. Don't let it discourage you. All right, we're going to put in 5 nodes. Let's union 1 and 2. Okay, so if you look here, the index at 1 and the index at 2 have the same thing. Now I'm going to union 3 and 4. It should say 0, 2, 2, 4, 4, 0, 2, 2, 4, 4. Now I'm going to union 0 and 2. It should make the 0th index equal to a 2. 2, 2, 2, 4, 4. And here's the big important part, right? If I union anything that's connected to a 2 with anything that's connected to a 4, I should just get a bunch of 4s, right? So let me union 2 and 4 together. I get a bunch of 4s. An array that looks like this means everything's fully connected. Now it doesn't matter what I tell it to union, by the way. It's always just going to return the array because everything is connected. And so just like that, we've got a way of telling if any points on a graph are connected without too much overhead. And so I don't think my exit command works if I put in 0. Yeah, it doesn't like that because it tries to run this command. And yeah, but anyway, the array itself is updating correctly, so we know we're okay. Okay, so far so good. Here is the strategy that we're going to be using to make this work. What if we just made nodes for all the points in our board, right? And then we made 2 extra nodes, just 2 extra nodes. And we connected the first extra node to everything in the first row, and the second extra node to everything in the bottom row. Then every single time I open a square, all I have to do is figure out what I need to connect it to, any adjacent squares that are open. And if the board ever percolates, I know that this top node shares a parent with this bottom node, because remember, the parents are always updating. And so we kind of have reduced this really complicated, weird divide and conquer backtracking problem down into just a simple graph problem. But we got to be a little bit careful. There's some things we want to look out for. So the basic logic loop, whenever we open places and make unions, right? We open a random spot. We check the cardinal directions, right? So we look above it, below it, to the left, and to the right. And if any of those are open, we're going to make a union. And that's the idea. But you have to be a little bit careful, right? We have some literal edge cases here. For example, if I take this value all the way on the right, at the rightmost edge, this value plus 1 is going to bleed over into the next row. That does not percolate. That's not what's supposed to happen, right? We need to make sure that they're in the exact same row. Also, we need to make sure that, like, what about the corners? If we ever subtract 1 or subtract n from these corners, we need to make sure that they are still in bounds. And so at this step, we want to make sure that making sure you understand we're working with 1D numerical values for all of these points. Hence, I can do s minus n, s minus 1. This is referring to s as in a spot, as in a one-dimensional bookkeeping method. And that's going to be useful because this whole union find technique works based off of integers being stored in an array. You could make them whatever you wanted and then do like hashing, but that's probably a little bit too advanced for right now and takes a lot more time. Okay. So we need to make sure that they're in the same row, right? That's not going to be as scary as it sounds. Let's go ahead and start writing the logic loop for this whole thing, right? I'm getting this started. Before I jump to that code, I want to make sure you guys see the big picture of what's going on here, right? If you generate a percolating board, right, we have a 2D array of all zeros. And in this 2D array of all zeros, we're going to keep opening random squares. And we're going to count those squares because they're going to tell us our ratio that we're looking for. And every time we open a square, we're going to check its neighbors. And if any of them are open, we're going to make unions. After we've made those unions, the board may or may not percolate. So we're going to check for percolation. Right? In other words, we're going to check to see if those extra 2 points that we've added are connected or not using the same union find technique that we defined earlier. Okay. So with that, let me first just write the percolation code at the bottom here, just so we know what we need. We have some idea of what we're going to need. So I'll leave some space for the helper methods I'm going to be using, but define percolation test. I'm going to give it a size n, right? The board is going to be equal to generate random board. I'm going to generate a board of size n. And I've decided I'd rather open spots progressively rather than have them open beforehand or use this function in any way. So I'm just going to pass in a 0. To be honest with you, that whole thing was just a trick to initialize for in your brains the way that I'm going to be opening spots. Okay. The board right now is all zeros. There's no open spaces. So we're going to make a Boolean variable called percolates. And this is equal to false right now. I'm going to call it percolates, not percolated. Okay. Now we need spots to open. We're going to use the exact same technique we used earlier. Spots to open is equal to a list of range n squared, right, which is going to give me an array from 0 up to n squared minus 1. That's how many elements I have total. And then I'm going to shuffle that, random.shuffle spots to open. That's how you shuffle an array in Python very easily. Okay, we need a parent array. This parent array is going to just be equal to initialize. Remember, I need 2 extra nodes. It's going to be n squared plus 2. That'll give me, now remember, this is going to give me n squared as an actual number and n squared plus 1 as an actual number. The last, we're including 0 for the beginners here, so everything's kind of downshifted by 1. And then we need a counter for how many spots that we've actually opened. So spots open is equal to 0. Okay. Now we want to connect all the things in the top row to all the things to our first extra node. And we want to connect all the things in the bottom row to our second extra node. And so we're just going to make a for loop here that'll do that math for us. So for I in range n, we're going to union I, so the 0 up through n minus 1 is the first row. And I in range n is going to give you 0 through n minus 1. So if I union I with the first extra node that I've made it, n squared, that's going to connect everything in the top row with the first extra node that I've made. And second, now I need to do everything in the bottom row. So this has been a little trick that maybe you all get very used to doing very shortly in like algorithms class or whatnot, if you've seen it. But the bottom right grid, the bottom right point on the board right here, this is not n squared, it's n squared minus 1. And then if I subtract 1 from it, I have this. And if I subtract 2 from it, I have this value right here. And so I can use a little trick here. I can do n squared minus 1, that's automatically the bottom right, minus I. And that'll go from the bottom right all the way to the bottom left, giving me the last row. I'm going to union that with the second new point that I've made. Remember to pass in the parent array. Right? Okay. This is how I'm going to generate all my unions. Now, the basic body of this program is, while this program doesn't percolate, so while not percolate, it's that easy in Python, we're going to open spots. So we know we want to make an open spot method, an open spot function. All right. It's going to take in the board. We know we're going to open the specific spots to open, and I'm going to reuse the counter for the number of spots open right here. I'm going to pass this spots open. Let's see. And then, this is the design phase. So when I think about what else do I want to give this? Well, I know I'm going to have to do some math with n to get to x and y. So for good functional style, let me also just give it n. So that way I can do all the math very easy. This function does not yet exist. So let's go ahead and write one. This right here is going to be the hardest part of the entire program. If I want to open a spot of the board of size n, this part right here is going to be the most sort of cumbersome to follow logically. But if we stick through this, we can do this, right? The element of the board that I'm going to be opening, the array that I'm accessing, same floor division trick as earlier, is spot floor division n. And y, right? How far across we're going to go for which element in the array. This is going to be spot mod n. And we're just going to set that area, or that spot, to a 1. That means we've opened it. Okay. This is the part where we think about what these unions look like. We need 2 different checks for checking the same row versus the same column. There's no weird edge cases for columns. The only thing that can happen for columns is that it can go out of bounds. It can be less than 0 or greater than n squared. And we need to check for that. But for checking if it's in the same row, it's actually not that bad. It's the same trick that we've been using this whole time to get the array that we're accessing. If I go back up to this slide right here, we can just make sure that the candidate or the place that we're unioning to, floor division, the size of the board, or the dimension of the board, if that's the same thing as the spot that we just opened, floor division, the size of the board, they're in the same row. So for example, 9 and 8 in a 4x4 grid, 4 goes into both of these evenly the same amount of times. Same for 10 and 11. Right? So that's actually not a really terrible check. And so we can just implement that very easily. We're going to make a function here as well. I'll put it above OpenSpot because I'm going to be using it in OpenSpot. Def in bounds. It's going to tell me if it's bigger than the board or less than the board, right? So in bounds is just going to take in n, right? And let's see, the candidate that I'm testing, that should work. So if it's greater than or equal to 0, it has to be greater than or equal to 0 and it has to be less than n squared. So return candidate is less than n squared and candidate is greater than or equal to 0. That's how we check if it's in bounds. Okay. We're going to break our checks for making our union down into 2 different candidate arrays. We're going to break east and west into one array and north and south into one array. And so if I break, that'll allow me to do my checks more elegantly. So here I'll do xcand. These are x candidates. I'll call it candidate plural, just make it look like English. X candidates is equal to whatever the spot was -1 and whatever the spot was +1. And then my y candidates is equal to whatever the spot was -n and the spot +n. Okay. Oh, we're going to have 2 different for loops, one going through x candidates and one going through y candidates. So for x candidate in x candidates, right, I got to do a couple of checks here. Right, first of all, is it in the same row? So if xcand floor division n is equal to the spot we just opened, floor division n, they're in the same row. And if it's in bounds, it should be in bounds. That's probably better. In bounds, we're going to pass it n and the candidate. Right? So if it's on the same row and it's in bounds, next we want to find out if it's open, right? We don't want to union points that are closed. That's kind of useless, right? So I have to figure out if it's open. But figuring out if it's open means doing the same index math. So I'm going to extract that to its own function. Def is open and the candidate that I'm checking. And same thing here. X is equal to candidate floor division n. Oh, I also need to give this the board, right? Because it needs to tell me if that value is equal to 1. I can learn to spell. Okay. And y is equal to the candidate mod n. And then I just want to figure out if that spot's a 1. So return board at x board at x y is equal to 1. That's all I need to do. Okay. So if that and if it's open, if is open, I'm going to give this n. We use n to check if it's open. I'm going to give it the candidate, which here is xcand. And I'm going to give it the board, and this will tell me if it's open. Great. Okay. If it's open and it's a valid point, we make a union. We're going to union the spot that we just opened with this x candidate. Remember to pass in the parent array. Okay. I didn't give this the parent array. That was an oversight. So we're going to be doing unions, right? So down here, to make sure that we do that, we gave it the board, and here I'll finally just pass it the parent array. Okay. We union the spot xcand, passing the parent array. And the logic for the y candidates is similar. Ycand in y candidates. But the difference here is we don't need to check if it's in the same row. There's none of that business. So if in bounds, we're going to give it n, the y candidate. And that's all we need for inbounds, I believe. That's all I should need. All right. N and the y candidate. If it's inbounds, and if it's open, and here we give it n, the candidate and the board. So y can and the board. Same thing. We're going to make a union. Spot, y can, passing in the parent array. That's all we have to do to get these unions. At the very end of this, just for elegance sake, we'll return the board. But you don't actually have to do this. If the board's getting permuted while it's inside this function, you don't have to return it to say that you've done this. But for you Java that's out there, I'll keep it like that. Okay. So I've written my open spot function. Let's see if it lines up apples to apples. I gave it the board, the spot, and in parent. I gave it the board, the spot to open, and in parent. Okay. I've opened a spot. Now I need to find out if it percolates, right? Okay. Remember, percolation just means 2 extra nodes we added are connected. So def does it percolate. And I just give it the board, or not even the board. I actually just need to give it the parent array. And I need to return the parent array in n, remember, because we need to figure out the n squared point and the n squared plus 1 point. So connected n squared and n squared plus 1. If they're connected, then this is true. Then it percolates. And so we're going to reassign percolates every time we do this to does it percolate, passing in the parent array and n. Then the spots we've opened plus equals 1. And at the very end here, remember, ultimate objective is to get a ratio of how many spots we've been opening. We're going to return the percolating board and the number of spots that we've opened divided by the size of the board, which is n squared. Okay, I haven't read through this. I did it all in front of you just now. So let's see if it works. Percolating board is equal to percolation test. I'm going to pass in, let's do a 5 by 5, 10 by 10 grid. And let me print percolating board at 0. That's going to give me the board. If it prints, then I know that it works. Okay. I use this connected function right here, but remember the connected function needs a parent. That's what it's using to check, right? We need to pass in the parent. Okay, it gave me an array. So let's use the same trick we used earlier to see if it'll plot this array for us, this board for us. And if it percolates, we'll be able to manually check it right here. Okay, and we're not going to generate a random board anymore. We're going to be using the percolating board. 0. Don't worry, guys, I'm almost done. Hit run. See how this works. All right, and as you can see, this board here percolates. If you take the top right area and you move this all the way down, this will make a pass from the top or the bottom row. Now, what's great about this is it's really efficient, right? Our checking for connections isn't a brute force algorithm. There's no recursion. There's no backtracking. We're just using an array. And so now we can start calculating that constant that we want. Remember, big picture, that's what we want. And so we're going to make a percolation approximation function, right? It's not that bad. Approx percolation. And this is just going to tell me how many, I'm going to give it a number of how many trials I want to run. It's going to take an average of the ratios across that many trials and what size board I want to be using. So let's make an array called ratios. I'm going to be storing the ratios that we get. And then for I in range trials, we're going to append to ratios. We're going to do the percolation test, right, using n. And we're going to append the first value that comes out of it. that's going to give us the percentage every time. And then we're going to return numpy.average. This is giving me the average of the ratios list. And I'm curious for the standard deviation, so numpy.standard deviation of ratios. Okay. And okay, now I'm going to do like 100 trials. Box percolation with 100 trials on a 10 by 10 grid. What the hell? I'll print the results, right? Just get a very basic test what this gives us. If I run this, 0.5873. Okay, let's try it on a bigger board as well, right? And see if we can do it on a 20 by 20. First of all, notice how quickly that ran. It did 100 different percolation tests, right? Oh, I don't need to be doing this anymore, this percolation test. I got 0.592975. All right, I'm gonna let you guys in on a secret. The percolation constant is a real thing in all those sciences I mentioned earlier. If you go to the Wikipedia page for the percolation threshold, and you scroll down to what it is for square boards, it's around 0.5927. You see that? And so if you don't believe me that this works, you can validate this constant or what it's doing across some more reputable sources if you'd like. All right, with that, this is a basic percolation test program. Now I have a challenge for you people, right? Anyone who's still here and be able to stick through all of this. I want you to color the board. I want you to color the board. There's many ways you can think about doing this, but the flowing water should be visualized somehow. I want you to change the color of the board to something to represent that. You will run into a problem. Right now our code, it's very easy to check if it percolates, but when you color the board, you run into something known as the backwash problem. And so as soon as one of these things down here opens, right, as soon as this point over here opens, the board will percolate, but it's also connected to all of these points. And so right here, you want to think about the blue squares as being connected to the top row because that's where water is coming from. But this square right here, these squares right here, they're not connected to the top row at all. They're connected to the bottom row, which after it percolates is connected to the top row. This is known as the backwash problem. And I want you guys to think about a solution to the backwash problem. Right? I'll give you some hints. Do we actually need 2 extra nodes? That's my first hint. Second, when should you color it? If it's connected to the top row or something else? These are the hints that I'll provide you for how you can efficiently solve the backwash problem. All right. Other than that, this was the first workshop hosted by the Developer Student Club at Rowan University. We have a references page here. I guess Scott used something from Mark Lutz's Programming Python. This is a great book. You should check it out. There's PDFs on the internet. But anyway, I want you guys to send an email to rowandevelopers.com if you solve the backwash problem, or if you just followed along here and did something different. Feel free to submit your solutions to us. And I would like some feedback. I know I have a tendency to talk quite fast or maybe not explain everything perfectly. I'd like to hear feedback so that we can improve for the future. Also, don't forget to RSVP to our TensorFlow workshop. Find that for you. All right. That's the link right here. And that's about it. Drop any questions you have in the Twitch chat, and we'll address them. If you're interested in being a part of the Developer Student Club, remember to hit up our website, rowandsc.com, join our Discord, our socials, check out what's on our GitHub, etc. I look forward to hearing from you. Sure. So here's the code that we have here. Here's our actual percolation code. what this is going to do is going to make a board that's completely blank at first. It's going to make us a list of all the places that I need to open in this board. And it'll go through this board, opening all the spots that are in this list in random order. Every time it opens a spot, it's going to check if it percolates. As soon as it percolates, this loop will no longer work, and it'll return the board and the spots. To solve the percolation problem, we circumvented the entire issue of brute force backtracking, etc., of checking if the top row is connected to the bottom row in any way, by implementing something known as a union find structure. The union find structure basically just keeps an array of parents for nodes on a graph. And so we can reduce this problem down to a graph problem. The way that we managed to do that, I defined that whole data structure up here: initialize, find, connected, and union. And whenever the board percolates, any two extra nodes that I've initialized, which are connected to the top row and the bottom row, are going to be connected. And so that's handled right here in does it percolate. So all I have, the main functions here, are open spot, percolates, and union, right? Opening a spot will figure out any candidates that you need to check to make any unions. And percolates will just tell you if the extra 2 points you have are connected. This footage will be uploaded to YouTube on our channel. I'm also going to send a mass email to everybody that came to this workshop or RSVP to this workshop with that link and other links that you can check out, along with this file, so for your own review. Okay, with that, thank you all for coming.